Hello everyone, welcome to the video lecture series of operating system. In today's session, we are continuing with the topic deadlock in operating system. Myself Kunal Panchal, your instructor. In this particular session, we are specifically going to discuss deadlock detection. In the previous session, we have seen the deadlock definition, the concept of deadlock with respect to real life examples, as well as with respect to operating system as well. Now, we are going to discuss the deadlock detection. As we know very well, a deadlock is one type of problem, and that should be avoided. Yes, so how we can avoid the problem of deadlock? So for that we need to identify whether system enters into a deadlock state or not. So how to identify it? So with the help of deadlock detection algorithm, we can come to know that whether this system is suffering from deadlock or not. So let us discuss deadlock detection in detail. So there are two types of deadlock detection algorithms are there. One is single instance deadlock detection algorithm, and second one is multiple instance deadlock detection algorithm. So what is single instance? Means a single system have more than one CPU. That type of scenario would be considered as multiple instance of the system of a same CPU, we can say. Yes, in the case of single instance, what it means? So if a system contains a single CPU, that type of systems we can consider as single instance system. Okay, and if a system contains more than one CPU, so that type of instance would be considered as multiple instances. Okay, so as far as single instance deadlock detection algorithm is concerned, that can be identified with the help of wait for graph. So what is wait for graph? So wait for graph is nothing but a variant of resource allocation graph, or we can say enhanced version of resource allocation graph. So what is resource allocation graph? That you have things in your mind. So we have already discussed in the deadlock introductory session what is resource allocation graph. So resource allocation graph contains 4 different components. That components we are going to discuss in later slide. So these things to keep in your mind. If a single instance resources we have, and if we want to identify whether deadlock is occur into the system or not, with the help of this wait for graph, we can come to know that the deadlock is there or not. As far as multiple instances is concerned, that detection we can identify with the help of Banker's algorithm. So the multiple instance deadlock detection algorithms we are going to discuss in the upcoming videos. How we can use the Banker's algorithm to identify whether the deadlock is present into the system or not. So in this particular session, we are looking for single instance deadlock detection algorithm, and in that case, we are using wait for graph. So as I told you, wait for graph means it is one type of graph, and you know very well graph contains set of vertices and set of edges. Yes, but it is nothing but the spatial version of graph. We can say that is wait for graph means what? In which the processes are waiting for the other processes for its execution. So let us discuss wait for graph and resource allocation graph with the help of one example. How we can identify whether the deadlock is occurred into the system or not. So let us discuss the single instance deadlock detection algorithm with the help of example. So, in this particular figure, as far as figure A is concerned, it is nothing but resource allocation graph, and figure B is nothing but wait for graph. So let us discuss first what is resource allocation graph and what are the different components we have in resource allocation graph, and then we will discuss how we can convert this resource allocation graph into a corresponding wait for graph. And then we can come to know that whether the deadlock is present in the system or not. So let us discuss resource allocation graph in detail. So as far as this figure A is concerned, so as I told you, there are four components of resource allocation graph. One is set of processes we have, that is enclosed with the help of your circle. There are set of resources we have, that is enclosed with the help of your rectangle, and there are two types of edges we have, means edges starting from process towards resource, that is nothing but request edge, and the edge starting from resource toward process is nothing but allocation edge. So there are four different components. One is set of processes, then set of resources, and two types of edges. One is request edge and second one is allocation edge. So now we can elaborate this resource allocation graph in detail. So you can see there are different processes we have starting from P1, P2, P3, P4, etc. And we have various resources we have. Yes, so you can see in the case of P1 process, so P1 is requesting a resource R1, but R1 resource is already acquired by P2 process. So it means what? Ultimately, P1 is waiting for P2 to release its resources. Yeah, same way, say for example, if you are talking about process P2, so process P2 is requesting resource R3, resource R4 and resource R5. Yes, so let us discuss P2 process is requesting R3 resource, but R3 resource is already acquired by process P5. Yes, so it is the P1 is waiting for something. In this case, P2 is waiting for something. Yes, say for example P3, process P3 is again waiting for one resource which is nothing but R5. Okay, and same way P4 is waiting for resource R2. So it means what? The P1, P2, P3 and P4 processes are waiting for resources. Means what? They are in waiting state right now. Okay. So once it acquires the resources, then it will be executed in the system. But right now, all the processes like P1, P2, P3 and P4 are in waiting state. Now what will happen? If I want to come to know that whether the deadlock is present or not, so as we have discussed, the necessary conditions of deadlock, which is nothing but mutual exclusion, golden weight, no pressure and circular weight. So there should be some a closed loop needs to be formed, or is a cycle needs to be formed, and then we can come to know that whether the deadlock is present or not. Means if a wait for graph contain a cycle, or we can say closed loop, and if you are talking about single instance of resources, definitely the deadlock will be present. But if you are talking about multiple instances of resources, in that case, if loop is, or if cycle is found, yes, so the deadlock may or may not present in that case. we cannot ensure, we cannot confidently tell that the system contains a deadlock. So this particular strategy or this technique or this algorithm is specifically work on single instance type of resources. It won't work in multiple instances of resources. Yes. So let us discuss. Is there any cycle is formed or is a closed loop is formed in the case of resource allocation graph? So we can start our journey from P1 process, P1 to R1. R1 is already acquired by P2. P2 again it will go to requesting R4 resource. Again it will go to P3. P3 to R5. R5 to P4 and P4 to R2 and again R2 will go to P1. So it means there is one cycle. So if closed loop is found in this particular graph, then we need to come to know that whether this cycle leads to a deadlock situation or not. So let us convert this resource allocation graph into corresponding wait for graph, and then we can conclude whether the deadlock is present or not. So how we can convert this resource allocation graph into wait for graph? So wait for graph is special type of graph, as I told you, which contains set of processes and set of edges. There is no resources are involved in the case of wait for graph. So how we can construct a wait for graph based on any resource allocation graph? So in this particular figure, let us discuss how we can convert it. So for example, if you look at resource allocation graph in which P1 is requesting R1, but R1 is already acquired by P2 process. So what will happen in this case? So ultimately, as I told you, P1 is waiting for P2. So if you ignore the resource which is already held by P2, so if you concentrate to only processes, so ultimately we can say that P1 is waiting for P2. So we can construct accordingly in the case of wait for graph in which P1 is waiting for P2. This one P1 is requesting P2. It means P1 ultimately P1 is waiting for P2 for its execution. Same way, in the case of resource allocation graph, P2 is requesting resource R4, but R4 resource is already acquired by P3 process. So in this case, what we can say that P2 is waiting for P3 process. So according to that, we construct P2 is waiting for P3 wait for graph. Same way, P3 is requesting a resource which is nothing but R5, but R5 is already acquired by P4 process. So it means P3 is waiting for P4. So we can construct accordingly in the case of wait for graph. Same way P4 is requesting for resource R2, but R2 is already acquired by P1. So what we can conclude from this? So P4 is waiting for P1. So in that case, you can construct accordingly. Same way P2 is requesting resource R3, but R3 is already acquired by P5 process. Yes, so P2 is requesting R3. Yes, but it is already acquired by P5 process. So ultimately we can say that P2 process is waiting for P5. So in this way you can construct the wait for graph. Now we need to identify, is there any closed loop that we found in this particular graph? If cycle exists, definitely there would be a deadlock in the system. So you can see, starting from, in the case of wait for graph, starting from P1 to P2, P2 to P4, and P4 to again P1, means what, there is a closed loop. Always a cycle is formed. So definitely this particular system leads to a deadlock situation. Okay, so in this way you can detect the deadlock in the system. So I hope it was clear to you. Thanks for watching this video. See you in the next one.